Hello everyone, and welcome to this first episode of the CTAIO Labs podcast. Quick intro to myself, your host. I'm Thomas Brammer, founder of CTAIO.dev, the destination for future tech leadership. I've spent over 2 decades in tech as a hands-on developer, engineering manager, CTO, CIO, working inside companies like Apple, Google, Netflix, Adidas, McDonald's, and the like. Today, I'm a thought leader and advisor for mostly Fortune 50 enterprises at that critical intersection of technology and AI to future-proof their businesses. In this podcast, we'll talk about a variety of real hands-on, pragmatic, real-world lab experience at exactly that intersection of technology and AI. To stay on top and secure your weekly AI edge, subscribe to my newsletter at CTAIO.dev and stay informed about new episode releases. And if you want to say hi or inquire about my advisory services for your enterprise, visit prommer.net. That's Prommer. Response is always guaranteed. So now, in this first episode, we're talking about creating your AI clone, starting with voice. It's a project I'm working on for a product in the personal branding space. I tested 8 different voice cloning engines: ElevenLabs, Cartesia, Coqui, LMNT, Fish Audio, Style TTS2, OpenAI, and Deepgram. Well, so you don't have to if you're short on time. We actually kick it off with playing you the best cloned voice that we got to. It's from our winner in this experiment, Cartesia. So you actually have a direct comparison to my now human voice to that cloned voice in a second. Then we hand it over to a deep dive generated with NotebookLM based on the full in-depth article posted on CTAIO.dev. Easy listening for your next commute, run, or wherever you are consuming your audio content. So let's get into it with the voice clone replay, and you'll hear me again before we wrap it up. Enjoy, and here's a snippet of my AI voice clone right now.
I am the clone voice of Thomas Brammer, generated by Cartesia's Sonic 3 engine from 54 minutes of studio recordings. What you're hearing is not a recording. It's an AI model that learned Thomas's speech patterns, intonation, and accent. This is exactly the kind of technology we explore on CTAIO Labs, the intersection of AI and technology, tested hands-on with real results you can hear for yourself. In the article behind this episode, Thomas tested 8 different voice cloning engines head-to-head. He compared quality, cost, training, data requirements, and multilingual support. The results were surprising. The open source option needed just 5 seconds of audio, while the winner needed 54 minutes, but produced a voice clone that fooled colleagues in blind tests. Now let's dive into the conversation generated with NotebookLM about his hands-on deep dive article on voice cloning.
Imagine logging into your computer tomorrow, typing, just a quick paragraph of text, and then hearing your own voice read it back to you.
Right, and not some robotic approximation either.
Exactly. Not a stilted Siri-like echo. Your exact voice, complete with your unique breath patterns, your regional accent, the specific way your pitch drops when you finish a sentence, all your little emotional tics.
Which is wild to think about, because we are actually at a point where the tools to replicate that biological cryptography of human speech are just sitting right on our laptops.
They really are. But if you are a tech leader who's actually trying to build this into a product right now, the marketing hype out there is, it's deafening.
Oh, it's completely overwhelming. Every single vendor landing page claims they have the most realistic, lowest latency, zero-shot model in the entire world.
Yeah, of course they do.
And for an enterprise developer or like a CTO trying to evaluate these claims, relying on that marketing copy is just a super fast track to a failed deployment.
Yeah.
The reality of the stack is way more complex, and frankly, it's a lot more fragile than the industry really wants to admit.
Which brings us to our mission for this deep dive. If you're a practitioner evaluating real-world voice AI adoption, this is your shortcut to the realities of the market. Today, we're unpacking this massive, incredibly detailed, hands-on experiment conducted by Thomas Brammer.
Yeah, and for context, he's a tech executive with over 30 years of enterprise-scale build experience. So he didn't just read the white papers.
No, he built the thing. He recently published an exhaustive, 18-minute technical read on his personal site, prommer.net, and for CTAIO.dev, where he detailed his honestly pretty brutal journey to build his own AI twin.
He really put it through the ringer. Tested 8 different voice cloning engines head-to-head. Same script, same speaker, same target output.
Right, and we're going to look at the honest trade-off today. The real limitations and the hard economics of doing this.
And the spectacular failures, too. Because when you put these models into a rigorous, controlled environment, Taking away the cherry-pick marketing demos, the assumptions that the whole industry operates on, they really start to fracture.
They really do. I mean, the hook here is that the undisputed market default, the platform everyone assumes is winning this race by a mile, actually lost Thomas's blind tests.
Yeah, that was a huge shock.
We're going to see how the open source community's offerings, while theoretically super powerful, have some deeply flawed mechanical quirks. Quirks that make commercial deployment incredibly tricky.
To say the least. And we'll also dissect how an entire voice AI company literally vanished overnight.
Yeah.
Just taking all its users' digital voices down with it.
Just gone. Okay, let's unpack this, starting with the biggest upset of the entire experiment.
So to really appreciate the upset, we have to establish the baseline. If you look at the current landscape of generative voice AI right now, ElevenLabs is the ubiquitous market default. It's the engine powering a massive percentage of automated YouTube channels, indie audiobooks, podcast dubbing, all of it. It supports 29 languages natively.
And you can spin up an instant voice clone in, what, a matter of minutes?
Literally minutes. From a mind share perspective, it's the Goliath.
Right. Like if you walk into a boardroom tomorrow and suggest voice cloning, somebody is inevitably going to say, just use ElevenLabs.
Yeah.
So Thomas set out to actually test that assumption.
Which is exactly what you want a practitioner to do.
He set up this strict blind A/B test. He took a standard homepage welcome script, about 1,100 characters, I think, and fed it into these different engines. But here is the critical part of his methodology.
Right, the listener test.
Yeah, he didn't just evaluate the outputs himself, because that introduces creator bias, obviously. He brought in 5 listeners who know his real voice intimately. Friends, family, people who know the exact micro ticks of how he speaks.
And he asked them to rank the synthetic outputs blind.
Exactly. And then, just to balance it out, he brought in 3 absolute strangers to rate the audio purely for naturalness without knowing what the real Thomas even sounds like.
It's a proper double-blind approach to subjective audio quality. It perfectly separates identity replication from just, pure acoustic naturalness.
And the results completely defied the market consensus. Out of those 5 blind tests, a relative newcomer called Cartesia Pro won 4 of them.
Which is wild.
It gets crazier. Thomas noted that his own wife could not distinguish the Cartesia clone from his actual biological recordings.
Let that sink in for a second. The Turing test for voice was passed not just for some random stranger, but for a spouse.
Meanwhile, ElevenLabs the Goliath tied for second place with this free tier platform called LMNT.
What's fascinating here is why this is so counterintuitive to how we typically view AI model dominance.
Right, because we just assume bigger is better.
Exactly. We're so heavily conditioned by the LLM space to believe that the platform with the most widespread adoption, the largest compute clusters, the massive venture capital war chest, that they must inherently possess the superior base model.
We just assume ElevenLabs has the smartest neural network.
Right, but Cartesia's approach to the problem is fundamentally different. They managed to produce a clone that's not only more consistent and human-sounding, but they did it while operating with under 100 milliseconds of streaming latency.
That's incredibly fast.
That latency metric alone is an engineering marvel, especially when you consider the computational weight of decoding raw audio in real time.
Let me push back on that framing a little bit, though, because as a practitioner listening to this, I have to ask, is Cartesia actually a smarter AI model intrinsically? Or is it just winning the test because it's being fed a fundamentally different, significantly heavier diet of training data?
That's the real question.
Because when you look at the actual parameters of Thomas's setup, he definitely did not treat these platforms equally. The input requirements he used were wildly asymmetrical.
That is the pivotal point.
Yeah.
And it bridges us directly to the reality of how these systems actually learn. It isn't necessarily that Cartesia possesses some magical underlying architecture that ElevenLabs lacks.
Right.
It's about the methodology and the sheer volume of the training investment. When we talk about cloning a voice, we have to talk about the data you feed the beast.
So let's look at the actual investment breakdown Thomas detailed in his piece. The disparity across the market is staggering.
It really is.
At the lowest end of the spectrum, you have the open source models, specifically Coqui XTTS version 2. To build a clone with Coqui, the system requires exactly 5 seconds of reference audio, just a single breath of speech.
5 seconds, it's almost nothing.
Then you step up to the middle tier. This is where ElevenLabs and LMNT sit. For their instant voice clone features, they ask for a short snippet, ranging from roughly 10 seconds to about 1 minute.
And Thomas provided ElevenLabs with a pristine 1 minute and 16-second studio clip, right?
And he did. But then we look at the winner, Cartesia Pro. To achieve that wife-fooling level of fidelity, Cartesia demanded 54 minutes of studio WAV files.
And we really should clarify what 54 minutes actually entails for the person recording it.
Yeah, it's not a walk in the park.
No, it's not just hitting record on a Zoom call and rambling for an hour. Thomas had to produce 32 separate, meticulously engineered files. We are talking uncompressed, 16-bit, 44.1 kilohertz lossless audio.
Which means you have to maintain consistent distance from the mic, consistent energy levels.
Consistent room acoustics across almost an hour of spoken word. It's exhausting.
Yeah.
And the processing job alone on Cartesia's end took 4 hours of dedicated GPU time to run.
So we have 5 seconds versus 60 seconds versus 54 minutes. For a CTO looking at resource allocation, that is a massive delta. Is it a linear progression? Like, does 54 minutes sound 54 times better than 1 minute?
No, not at all. And this is where we have to understand the logarithmic curve of training data volume in machine learning, specifically for audio synthesis.
Okay, break that down.
The value of the data you provide doesn't scale linearly. It's a steep cliff followed by a massive plateau.
So what's actually happening inside the neural network at those different milestones?
Let's trace the curve. Moving from 0 data to a mere 5 seconds of reference audio yields an astronomical leap. You go from a generic robotic text-to-speech voice to an output that broadly captures your fundamental pitch, your vocal cord frequency, and your basic timbre.
Right, you sound recognizably male or female, deep or high-pitched.
Exactly. Now, if you push that 5 seconds to 60 seconds, which is the ElevenLabs instant clone sweet spot, you see another steep gain. The model now has enough context to capture intelligibility, the way you hit your hard consonants, and some basic pacing.
So it starts to sound remarkably like you on a really good day.
Yes, but after that 60-second mark, the curve flattens out aggressively.
The law of diminishing returns kicks in.
Severely. And Thomas actually proved this in his testing. He found that ElevenLabs hit a hard quality ceiling at approximately 76 seconds of input data.
Oh, wow, just over a minute.
Yeah. And he tried to force the issue, too. He utilized their professional voice clone tier, which allows users to upload hours of data. But adding all that extra audio moved the needle less than 5% in his blind listener tests.
So the model just hit a wall.
Exactly. It couldn't extract any more meaningful stylistic nuance from the additional hours of tape.
But wait, if ElevenLabs plateaus at just over a minute, why on earth does Cartesia demand 54 minutes? What is Cartesia doing with that extra 53 minutes of audio if the learning curve is supposedly flat?
Because Cartesia is executing a fundamentally different type of machine learning process. It's the difference between in-context inference and dedicated fine-tuning.
Okay, define those for us.
When you hand ElevenLabs a 1-minute clip, it's generally relying on in-context inference. The model looks at your short clip in real time, extracts the acoustic features, and dynamically extrapolates your voice based on its massive pre-existing generalized knowledge of human speech.
So it's guessing. It guesses how you would say a word based on how millions of other people say that word.
Precisely. Cartesia Pro, however, takes those 54 minutes and runs a dedicated, intensive training job specifically on your unique phoneme distribution.
I want to make sure I grasp the practical difference there. It sounds like comparing two different ways of commissioning a portrait from a brilliant sketch artist.
Okay, I like that. Go on.
Giving ElevenLabs a 1-minute audio clip is like handing that artist a really clear, high-resolution Polaroid of your face and saying, draw me reacting to a surprise or draw me laughing.
Right. And they're going to do a great job because they know the anatomical rules of human faces and they have your photo for reference.
Exactly. But giving Cartesia 54 minutes of lossless studio audio is like inviting that exact same artist to come live in your house for a week. They aren't just looking at a static reference, they are studying exactly how your specific facial muscles twitch when you're confused.
Yeah.
They watch how the light hits your jaw when you look down.
Right.
It is a fundamental mapping of your unique microexpressions.
And translated to audio, those microexpressions are your phonemes. Cartesia maps the exact microscopic ways your tongue and lips interact to form specific vowel and consonant combinations over a vast array of linguistic contexts.
That makes total sense.
Because it's lived with your voice for an hour, it doesn't just know what your voice sounds like in a vacuum, it knows how you behave acoustically over time, across different emotional states.
Okay, discussing the theory of in-context inference versus fine-tuning is great, but we really need to physically prove that.
We do.
And we have the actual raw audio files from Thomas's experiment. We are going to play the exact training inputs he fed into these systems and then immediately follow them with the AI-generated outputs.
This is where the rubber meets the road.
Let's start with the market default. Let's hear the quality of the short 1-minute clip Thomas provided to ElevenLabs. And here's what the training input sounded like.
ElevenLabs 10-sec studio recording input.
Okay, so that is a very clean, professional recording environment. Good pacing, clear articulation.
Very standard corporate baseline.
Now let's hear what ElevenLabs actually sounds like.
ElevenLabs output.
So the immediate takeaway there is the sheer polish. It's highly intelligible, the pacing is commercially viable, and it undeniably captures the core essence of Thomas's vocal texture.
It sounds good.
For 90% of basic corporate use cases, that output is totally acceptable.
It is good, but we have to add context here. Thomas didn't just accept the raw output. He used specific tuning profiles. He applied the excited and confident sliders within the ElevenLabs interface.
Right.
He specifically noted setting stability at 0.55 and clarity at 0.85 for the confident profile. But even with that manual tuning, as a listener, there's something slightly off about it.
Yeah, it suffers from what audio practitioners refer to as AI smoothness.
AI smoothness.
Yeah. Real biological human speech is chaotic. It's full of micro imperfections. We have slight hesitations while searching for a word, tiny moments of vocal fry at the tail end of a long breath, and unpredictable spacing between complex syllables.
Nobody talks perfectly.
Exactly. But ElevenLabs, because it operates so heavily on in-context inference over a generalized neutral base model, tends to iron out all of those imperfections. It acts like an aggressive audio compressor.
So it sounds like Thomas, if Thomas were a flawless, slightly over-caffeinated radio broadcaster who never needs to take a real biological breath.
That is perfectly said. It's impressive technology, but it lacks the grit, the friction of a real human being sitting in a room talking to you. It feels synthetic because it's too perfect.
Now let's contrast that polished inference with the winner of the blind test. Remember, this next engine ingested 54 minutes of audio to build its dedicated phoneme map. Let's hear a sample of that intensive, high-fidelity input data, and here's what the training input sounded like.
Cartesia Pro 45-sec sample input.
So again, pristine studio quality, very similar acoustic environment to the first clip. Now let's hear what Cartesia actually sounds like.
Cartesia Pro output.
Wow. I mean, the difference in the acoustic texture is just remarkable.
It is distinctly, undeniably more human. You can actually hear the natural intonation valleys, the way the sentences breathe and settle.
It completely lacks that glossy artificial sheen that ElevenLabs produced.
It doesn't sound like a broadcaster reading a script. It sounds like Thomas casually explaining a concept to a colleague over coffee.
And here's the fascinating technical nuance about that specific Cartesia output, which really highlights the difference in the training models.
What's that?
Because Cartesia trained so deeply on his 54 minutes of data, it actually learned his true baseline prosodic style. It learned his natural rhythm and his default emotional resting state.
Okay.
Thomas noted in his technical breakdown that with Cartesia, if you try to apply artificial emotion parameters like you do in ElevenLabs to make it sound excited or sad, it actually degrades the quality of the output.
Wait, hold on. You're saying adding emotion makes the Cartesia clone sound worse? Why would a more advanced model penalize you for using emotion tags?
Because the model already possesses a highly complex, multidimensional map of how Thomas naturally expresses emotion, built from almost an hour of real contextual data.
Oh, I see.
When you inject an explicit emotion parameter at inference time, you're essentially forcing the mathematical model off its learned parameters. You are injecting additive noise into a perfectly good signal.
So the model already knows exactly how he naturally speaks, and trying to manually override that behavior with a generic slider just confuses the output and introduces artifacting.
Exactly.
That tracks perfectly with the sketch artist analogy we used earlier. ElevenLabs needs you to turn the emotion sliders because it's guessing his emotional state based on a 1-minute neutral clip. It needs direction.
Yep. And Cartesia doesn't need to guess. It already knows his emotional range.
Okay, we have heard the 1-minute inference and the 54-minute fine-tune. Now let's look at the other extreme, the absolute bare minimum of training data.
This should be fun.
We are talking about Coqui XTTS version 2, the open source model that only requires 5 seconds of audio. Just 5 seconds. And here's what the training input sounded like.
Coqui XTTS 5-sec reference clip.
I mean, it is literally just a passing breath of audio. Barely a full sentence. Okay, let's hear what Coqui XTTS actually sounds like.
Coqui XTTS output.
Wow. Okay. where do we even begin dissecting that?
Well, from an enterprise deployment perspective, there are quite a few fatal anomalies in that audio.
I mean, just on a surface level, the AI completely hallucinated his name. It called him Thomas Farmer instead of Promer.
Which is a disaster.
And then a few seconds later, when it tried to read his website URL, promer.net, it completely broke down and spelled it out phonetically as bromer.net. That is a massive fail.
Yeah, if you are a tech leader and your CEO's AI twin cannot pronounce the name of your own company, that model is dead on arrival. You cannot deploy that.
You'd be laughed out of the room.
The pronunciation hallucinations are bad. But I really want to focus on the underlying acoustic characteristics because they reveal how the technology actually works. Did you notice how incredibly slow the speaking pace was?
It was painfully slow.
Thomas reported the exact metrics for this. For this specific 18-word script, the commercial engines ElevenLabs and Cartesia read it in about 20 to 22 seconds. Coqui took 76 seconds to read the exact same text.
It sounded like the audio was wading through molasses. And the other glaring issue, Thomas is German-American. He has a very slight natural accent in his English. But the Coqui output seemed to take that subtle accent and just amplify it massively.
It became almost a caricature.
Yeah, the accent bled heavily into every single syllable.
And those two specific auditory anomalies, the incredibly slow duration and the heavy accent bleed, are not just random software bugs. They are the perfect gateway for us to explain the deep technical mechanics happening under the hood at layer 1 of these voice generation systems.
I want to get into this. Let's look under the hood. As a developer, what exactly is the engine doing computationally with that tiny 5-second clip?
Right, so to understand why Coqui failed so spectacularly in this test, we need to talk about speaker embeddings. When you feed a 5-second audio clip into a zero-shot model like Coqui XTTS, the first step is running that audio through an encoder network.
Okay.
The encoder's job is to extract what is called a speaker embedding. In the case of Coqui, this results in a 512-dimensional vector.
Let me pause you right there. A 512-dimensional vector. For those of us who haven't taken advanced linear algebra in a while, what does that actually mean in the physical context of a human voice?
Right, sorry. The best way to visualize it is to imagine a massive audio control board with 512 individual sliders. Each slider represents a highly abstract mathematical representation of an acoustic feature.
Okay, I'm picturing the soundboard.
And we aren't just talking about bass and treble. We're talking about pitch variations, harmonic structures, vocal tract resonances, and something called formant transitions.
Formant transitions.
Yeah. Formant transitions are the specific acoustic frequencies created by the physical shape of your vocal tract as you move your tongue and lips to form vowels.
Got it.
When the AI listens to those 5 seconds of audio, it analyzes those formants and sets those 512 sliders to specific numerical positions to create a mathematical recipe or fingerprint of your voice.
Okay, I follow the concept of the soundboard recipe.
Yeah.
But if it successfully extracts the recipe of his voice, why did the output sound so heavily unnaturally accented?
Because that 5 and 12-dimensional embedding only encodes acoustic features. It does not encode phone mappings or the grammatical rules of language. Thomas has a slight German accent. Biologically, that means his vocal tract produces certain frequencies and formant transitions that are unique to that accent structure. The 5 and 12-dimensional embedding captures those exact acoustic frequencies perfectly from the 5-second sample.
But then what goes wrong?
Here is the flaw. When you ask the model to generate brand new English text, it applies that exact acoustic texture to every single word. The zero-shot model never learns what a neutral version of your voice sounds like.
It just blindly copies the acoustic texture of the sample.
Precisely. Therefore, the accent bleeds into everything. In fact, if you ask Coqui to speak Spanish using Thomas's voice, it would sound exactly like a German person speaking Spanish.
That is fascinating. It's essentially taking the physical, biological shape of his vocal cords from that exact 5-second window and aggressively, stubbornly mapping it onto whatever text comes next, regardless of context or language.
Exactly.
But what about the speed? The embedding explains the accent, but why did it take 76 seconds to read a 20-second script?
That anomaly comes down to how open source models handle duration prediction. Both Coqui XTTS and another open source model Thomas tested, Stella TTS2, utilize an architecture called an autoaggressive decoder.
Okay, and what does that mean for speed?
In these specific setups, the speed at which the model speaks is computationally decoupled from the speaker embedding.
Wait, so the AI mathematically knows what your voice sounds like, but it has absolutely no idea how fast you naturally talk.
Precisely. The module that predicts the duration of the speech is trained on the model's base corpus, the thousands of hours of generic public domain audio it was originally trained on.
Right.
The speaker embedding those 512 sliders only shapes the timbre, the tone, and the pitch. The model dictates its own tempo based on its underlying base programming, completely ignoring the pacing of your specific reference clip.
That is wild.
Yeah, that's why Coqui took 76 seconds and Style TTS2 took 84 seconds. For a script that the commercial engine zipped through in 20 seconds, the commercial engines actively sample and replicate your pacing from the reference audio. These specific open source models do not.
If we connect this technical deep dive back to the bigger picture, this fundamentally changes how an enterprise user has to interact with these different tools. It explains the entire philosophical and operational difference between the platforms we just listened to. ElevenLabs is essentially built as a blank slate. It has a neutral base prosody, meaning it has no preconceived notion of your emotional style. That is why those stability and clarity sliders work so beautifully. You are taking a neutral piece of synthetic clay and manually sculpting it into an excited or confident shape.
That's a great way to put it. And Cartesia, conversely, is not a blank slate.
Yeah.
Its foundational mathematical understanding of how to speak is your actual biological speaking style.
The clay is already perfectly sculpted to look like you before you even type a word.
Right.
So hitting an emotion slider on Cartesia is like taking a perfectly finished, hardened clay sculpture and trying to forcefully mold it into a different pose. You're just going to break the structure. You are adding noise and artifacts to a stable system.
That highlights exactly why fine-tuning yields a vastly superior clone, but also demands a totally different approach to prompting and generation from the developer.
Here's where it gets really interesting, though. We spent time dissecting the high-end 54-minute Cartesia fine-tune, and we've analyzed the struggling 5-second open-source Coqui model. But Thomas found a massive disruptor sitting right in the middle of the market, offering something kind of unbelievable on a free tier.
You're talking about LMNT.
Yes, LMNT. It quietly tied for second place with ElevenLabs in the blind subjective tests. And here is the kicker for developers. It is a zero-shot cloner. It only requires a 5-second to 15-second clip, just like Coqui.
But unlike Coqui, the output was highly recognizable, it had natural pacing, and crucially for anyone building applications, it offered sub-200 millisecond streaming latency.
And on top of all that, they offer 15,000 characters of generation per month entirely for free, with unlimited voices and no credit card required to start building.
Which completely flips the script on the barrier to entry for voice AI. It proves that you don't necessarily need the heavy 54-minute fine-tuning mechanics of Cartesia just to get a highly functional, basic zero-shot clone. If you are a startup experimenting with real-time conversational agents, and you absolutely need that sub-200 millisecond response time without burning thousands of dollars in API credits on day one, LMNT is presenting an incredibly compelling value proposition to the market.
It's the ultimate sandbox for tech leaders who want to prove the concept to their board before securing a massive budget. But, as Thomas rigorously points out in his deep dive, generating the perfect audio file, whether you use Cartesia, ElevenLabs, or LMNT, is really only the first step.
Oh yeah, it's just the beginning.
Because once you have that perfectly generated audio, what do you actually have in your hands?
You have a raw MP3 or WAV file sitting on a server.
Exactly. And for a tech leader trying to build a scalable enterprise solution, a raw MP3 sitting on a hard drive is not a product. It is merely a component.
It's a single puzzle piece.
To actually deploy this technology, you have to understand that voice generation does not exist in a vacuum. It is part of a much larger, highly interconnected, and often frustrating ecosystem.
Thomas breaks this ecosystem down beautifully into a 3-layer voice AI stack. If you're a CTO evaluating adoption, you cannot just look at the voice engine. You have to think across all 3 layers simultaneously, because a failure at any one layer breaks the entire product.
Let's walk through the architecture of that stack.
Sure. Layer 1 is what we have spent all our time discussing so far, voice generation. This is the TTS text-to-speech and cloning layer. This is your Cartesia, ElevenLabs, LMNT, or Fish audio.
You have to lock in this engine first, right?
Exactly. Because everything downstream depends entirely on the specific API design, the latency limits, and the exact audio format this layer spits out.
Okay, so layer 1 generates the high-fidelity MP3. Then we move to layer 2, which Thomas defines as lip sync and avatars. Because let's face it, in a modern enterprise context, audio alone is rarely enough.
No, you want video.
You want a talking head for your training modules. You want localized video for marketing. This is where platforms like HeyGen, SyncLabs, DID, and Rask AI come into the pipeline.
And this layer is notoriously tricky and computationally expensive. You're taking the synthetic audio from layer 1 and forcing a visual AI model to mathematically map realistic mouth movements to those synthetic phones, frame by visual frame.
Thomas actually walked through his exact literal production integration flow for his website. He didn't just write a theoretical white paper. He built the pipeline.
And he found all the pain points.
He started by generating the perfect voice track in Cartesia. Then he took that MP3 and ran it into layer 2. He presented 2 different paths for executing this, and both have serious friction points.
Path A is utilizing a platform like ElevenLabs. This is pure lip sync. You provide a pre-recorded video of yourself sitting silently or talking about something completely different, and you provide the new Cartesia audio track.
And ElevenLabs visually alters your lips and jawline in the source video to match the new audio.
Exactly.
And he dropped a really crucial in-the-weeds pro tip here for anyone attempting to use ElevenLabs. The default temperature setting in their API system is 0.5.
Right, which usually controls randomness or creativity in generative AI.
But Thomas found that dialing that temperature down to 0.3 produces significantly better, more natural visual results. It reins in the visual hallucinations, stops the jaw from looking distorted, and keeps the mouth movements tighter and more realistic.
That is the exact kind of practitioner knowledge you only acquire from actually building the stack and failing a few times.
So what's path B?
Path B, for layer 2, is generating an entirely synthetic avatar from scratch using a platform like HeyGen. Instead of altering an existing video, HeyGen builds a digital 3D puppet of you from a source video and animates the entire head and body from scratch based on the audio input.
But there's a workflow catch there, too. Thomas noted that if you use HeyGen's creator plan, the captions are not burned into the final video. You get a clean video file.
Which means you then have to take that massive video file, export it into another tool entirely like CapCut or Premiere to manually generate and overlay the subtitles.
So the automated pipeline gets longer and requires human intervention.
Which brings us to layer 3, distribution. This is the final mile of the stack. This is how the content actually reaches the end user.
It could be custom website video embeds, interactive IVR phone trees for customer support, podcast hosting platforms, or custom web apps orchestrating the whole thing via WebSockets.
Think about the complexity of what we just described. Generate voice in Cartesia via API. Send payload to ElevenLabs for lip sync. Download video. Upload to CapCut for captions. Export video. Distribute via custom website embed.
It's a fragmented assembly line.
It really is, and it begs a very serious question. Why go through all this effort? Why not just have the CEO sit down in front of a camera and record a video the old-fashioned way? What is the actual hard ROI for a tech leader to authorize building this 3-layer stack?
The primary ROI is entirely about decoupling content creation from biological constraints. Thomas lists several massive advantages for the enterprise.
The first one being true omni-channel scale.
Yes. Once the baseline clone and the avatar are built and validated, you can generate a 15-second TikTok clip, a 2-minute corporate explainer for investors, and a 30-minute internal HR training module simultaneously just from typing into a text document.
You are infinitely scaling video production without ever needing to coordinate schedules, book a studio, set up 3-point lighting, or suffer through multiple takes.
You can rewrite a script at midnight because the legal team caught an error, and regenerate the final perfect video in 3 minutes. You iterate at the speed of text, not the speed of production.
Second is massive global reach. Your English voice clone, especially with the base models rapidly improving their multilingual capabilities, can speak German, Spanish, French, and Portuguese.
It maintains your exact vocal identity in timbre, but uses native pronunciation and cadence.
You instantly become a polyglot brand ambassador without taking a single language class.
And lastly, it's about preserving a unified brand voice. Imagine customer support bots, interactive product tours, and automated phone agents. They all sound consistently like the founder or the chosen brand voice, 247, 365 days a year. It's an always-on, untiring digital representative.
However, relying on this 3-layer assembly line introduces a massive structural vulnerability to your business.
Oh, definitely.
When you build a complex automated pipeline where layer 2 inherently relies on the API outputs of layer 1 and layer 3 relies on the video outputs of layer 2, you're placing enormous existential trust in the stability of your third-party vendors.
Which brings us to the most sobering part of the deep dive, and frankly, a cautionary tale that every CTO needs to hear. What happens when the foundational layer 1 just collapses underneath your business overnight?
It's a disaster.
Let's talk about the absolute disaster of PlayHT.
PlayHD was not a fringe startup. It was a very popular, highly regarded voice generation platform. A significant number of startups and mid-market enterprise teams integrated PlayHD's API as their Layer 1 foundation.
They built their entire application architectures around PlayHD's specific latency profiles and audio formats.
Then, in July 2025, Meta acquired PlayHD. Now, typically in the tech world, when a giant like Meta acquires a tool you use, it might signal stability, deeper pockets, or better server infrastructure.
But that is not what happened here. By December 2025, just months after the acquisition closed, Meta completely shut the platform down.
And this wasn't a graceful, enterprise-friendly sunsetting where developers were given a 12-month roadmap to migrate their systems. It was a hard, brutal stop.
Thomas highlights the grim reality of this event in his piece. Today, if a developer's application tries to ping the PlayHD REST API to generate a voice, it doesn't return a helpful migration message or a redirect. It returns a harsh HTTP status code, 410, gone.
410 gone. That is a chilling response code for an engineer to see in their server logs. It doesn't mean not found right now. It means this resource is intentionally dead and it is never coming back.
It's the ultimate nightmare scenario for technical debt. And the worst part isn't just rewriting the API calls.
No, not at all. Any voice clones that users had spent hours training, perfectly fine-tuning, and storing on PlayHD servers are completely, irrevocably unrecoverable.
The underlying training data is gone. The proprietary mathematical models are gone.
If you built a custom Heijian avatar in Layer 2 that relied on pinging that specific synthetic voice from PlayHD, your avatar is now permanently mute.
It is the starkest possible warning about data sovereignty and vendor lock-in in the generative AI space. If you are a tech leader listening to this, and by some miracle a PlayHD integration is still lingering somewhere in your legacy codebase, you must migrate immediately.
Thomas specifically points to ElevenLabs and Fish Audio as the closest architectural replacements for those stranded by the shutdown.
But looking at the PlayHD disaster really forces you to consider the philosophy of digital ownership. You don't actually own your AI clone, you just own a temporary API key.
That is the brutal truth of the cloud AI era. You are merely renting access to a mathematical representation of your own identity. If the digital landlord decides to sell the building to Meta, and Meta decides to bulldoze it, you are left standing on the street with nothing.
Wow.
This is why having your original high-quality training data, those 32 lossless WAV files, securely backed up locally on your own iron, is absolutely critical. You have to be architecturally ready to rebuild Layer 1 on an entirely new engine at a moment's notice.
Given those severe risks, the constant threat of vendor shutdown, the wildly varying acoustic quality of the models, the sheer complexity of integrating a 3-layer stack, how does a tech leader actually sit down, build a spreadsheet, and budget for this?
That's a great question.
How do you choose your stack without getting burned financially or technically? Let's look at the real costs, because Thomas laid out his entire production budget down to the exact dollar.
And this is where the theoretical hype finally meets the CFO's spreadsheet. Let's break down Thomas's $127 a month production stack.
Okay, $127 a month. Here is exactly what that buys you in today's market. For Layer 1 voice generation, you have a choice. ElevenLabs starter tier at $5 a month, or the premium Cartesia startup plan at $21 a month. Let's use the Cartesia plan for the high-end output calculation.
Okay, $21.
Then, for Layer 2 avatars and lip sync, he is paying $29 a month for Heijian Creator, $49 a month for Sync Labs Pro, and $23 a month for DID Elite for specific photo-to-video capabilities. You sum all those subscriptions up, and you get roughly $127 a month.
On the surface, spending $127 a month across 4 different fragmented AI subscriptions might seem messy or unnecessarily expensive for a solo practitioner or a small startup trying to stay lean.
But Thomas distills this monthly cost down to a killer metric that completely reframes the enterprise value proposition.
Yes, he calculated the cost per finished minute of video. When you maximize those API quotas across the entire stack, it boils down to about 17 cents per finished minute of generated video.
Tater is 17 cents per minute.
This raises an important question for any decision maker or budget owner. What is your current cost per finished minute using traditional video production?
It is astronomically higher. If you were sitting there looking at your marketing budget, think about this. A traditional shoot requires the hourly rate of the on-screen talent, the videographer day rate, the studio and lighting rental, the audio engineer, and the post-production editor for color grading and cuts.
It adds up fast.
A single, high-quality, 2-minute corporate explainer video can easily cost $5,000 and take 3 weeks of back-and-forth revisions to deliver. Here, You are paying 17 cents a minute, and you can generate the final cut in your pajamas at 2 a.m. on a Tuesday.
The economics are undeniably disruptive to the traditional agency model. But to achieve those economics without sacrificing quality, you have to choose the right engine for your specific technical use case.
And Thomas provides a brilliant, pragmatic decision framework based on his extensive testing.
Let's run through that framework, because this is the playbook. Scenario 1. You need your exact voice cloned, and you actually have corporate budget to spend. What do you do?
Well, if your use case prioritizes absolute audio fidelity, naturalness, and conversational nuance above all else, you go with Cartesia Pro and invest the 54 minutes of studio time.
But if your use case prioritizes a vast interconnected ecosystem, 29 built-in languages for global rollout, and fast BIM motion tweaking via sliders, you deploy ElevenLabs.
Scenario 2. You need your voice cloned, but you have zero budget. You are a bootstrapper, or you're trying to build a proof of concept for a hackathon.
This is where LMNT shines. It is unequivocally the best free tier voice cloning available right now with its 15,000 free characters.
And if you want to avoid cloud APIs entirely and have serious technical chops,
you can run Coqui XTTS locally on your own NVIDIA GPU, completely free, though you accept the significantly lower output quality and latency issues.
Scenario 3. You are highly privacy sensitive. Maybe you are in healthcare, legal, finance, or you just strictly refuse on principle to upload your biological vocal data to a third-party server.
Then you are entirely restricted to open source models that you can run locally. Style TS2 or Coqui XTTS. The audio generation happens entirely on your local machine. The biometric data never leaves your hard drive or your private VPC.
Scenario 4. You are building real-time agents, AI phone bots, live customer service interactives, or dynamic video game NPCs.
In this scenario, streaming latency is the only metric that matters. If the bot takes 2 seconds to process and reply, the human caller assumes the line is dead and hangs up. You need LMNT for its sub-200 millisecond response times, or you upgrade to Cartesia's specialized sonic model for sub-100 millisecond latency.
And finally, scenario 5. You actually don't need a custom voice clone at all. You just need high-quality text-to-speech reading your text dynamically.
Then you skip the complex cloning models entirely. Use OpenAI's TTS. It's incredibly cheap at about 2 cents per run, highly reliable, and has the simplest API in the industry. Or use Deepgram, which offers a generous $200 in free credits for excellent pre-built voices.
It is a fantastic zero-fluff matrix for decision makers. But Thomas also looks ahead in his analysis. The technology and the API stacks we're discussing today are a snapshot of early 2026. What does the landscape look like 12 to 18 months from now?
The technological trajectory is incredibly steep. First, flawless multilingual cloning without any accent bleed will become absolute table stakes. Enterprise clients simply won't accept an engine that makes their CEO sound like a caricature when delivering a message in Spanish.
Right.
Second, the massive shift from asynchronous content creation to synchronous live interaction will accelerate. We are rapidly moving from batch processing an MP3 for a YouTube video to deploying an always-on, real-time conversational agent that sounds exactly like a human, orchestrated dynamically by specialized audio routing tools like LiveKit and Vappy.
So what does this all mean? If we synthesize everything Thomas Prommer uncovered in this exhaustive deep dive, the technology has undeniably crossed the uncanny valley.
It really has.
The outputs are no longer robotic novelties. They are production-ready assets capable of fooling family members and replacing studio time. But achieving that level of success requires navigating a profoundly complex, fragmented ecosystem.
You have to deeply understand the logarithmic value of your training data, knowing mathematically that 54 minutes of studio audio yields a fundamentally different model than a 5-second iPhone clip.
You have to master the friction points of the 3-layer stack of generation, lip sync, and distribution. And above all, you have to architect your workflow to survive the inevitable shock of vendor lock-in and platform collapse.
And the reality of that fragile ecosystem points to a final, slightly provocative conclusion that builds directly on what Thomas is projecting for the future of the industry.
Let's hear it.
As these foundational models, the ElevenLabs, the Cartesias, the LMNTs, continue to rapidly improve and copy each other's breakthroughs, the underlying AI architecture itself will inevitably become commoditized. Within a few years, almost any decent engine will be able to perfectly synthesize a human voice given the right parameters.
So if the software engine is no longer the differentiator, what is?
The data. When the algorithms are ubiquitous, equal, and cheap, the only competitive moat left standing for an individual or an enterprise will be the purity, the volume, and the exclusive quality of your training data.
Which means we are entering an era where your personal, studio-grade vocal recordings, those 32 lossless WAV files capturing the exact micro-expressions of your biological cryptography, might soon become your most fiercely protected intellectual property. It is the new gold standard of digital identity.
Absolutely. The model is temporary. The biometric data is forever.
A huge thank you for joining us on this deep dive. Whether you're building an enterprise solution for a Fortune 500 company or just experimenting with your own AI twin on a weekend, we hope this gives you the pragmatic, hype-free roadmap you need. Until next time, think very carefully about where you leave your digital fingerprint.
Hello again. So that's it for episode 1 of the CTAIO Labs podcast. Thank you so much for listening to this premiere episode. The full article with the comparison table, all 8 engine rankings, and the audio demos you can play for yourself is available now at ctaio.dev. So head over there, link in the show notes. Next episode, we go from voice to video, building the full AI clone with lip sync and avatar generation. So that's where things get really interesting visually. Subscribe on Apple Podcasts, Spotify, YouTube, or wherever you listen so you don't miss it. If any of this saved you time, share it with one of the persons who's building in this space. I'm Thomas Farmer. This is CTAIO Labs. See you next episode.